Sir, உங்களோட voice unmute பண்ணப்பட்டிருக்கு. Sir. Sir. Sir, sound கேக்குது இல்ல sir. Unmute பண்ணப்பட்டிருக்கு.
Okay, so hope now you all can hear me. Right, so last time this is what we defined, right? So we defined a polynomial phi such that phi of q comma z is equal to rho of z minus q times sigma of z. And then we see that if the roots of this polynomial satisfies the Dahlquist root condition, which is the absolute modulus, or the absolute value of the root is less or equal to 1 for all roots. And if the absolute value is equal to 1, then that root should be simple, right? So that is what we define as the condition for absolute stability. So here, one thing you can notice that is when you are trying to solve this polynomial and try to compute its roots, you can observe that somehow q is going to be a part of the root, right? Because there is a unknown variable q, and you all know that q is lambda times h, and lambda is a complex number. So this complex number is going to be the part of almost all the roots, right? So, or at least some of the roots. So then, in order to satisfy this Dahlquist root condition, right, we need to have certain restrictions for that complex value q. So those complex restrictions we have on these complex values q basically can be interpreted in a complex plane, right? So imaginary and real plane. So then it can be a region or it can be an interval. It depends on whether it is a complex number or real number or things like that. So once you know that there is a restriction on q, you can interpret that restriction in a complex plane, that is imaginary and real axis, right? So that is the complex plane. So and then you can draw the region or you can interpret the region. So that region is called the stability region. And then that once you draw that region in the complex plane, you always have a certain interval in the real line or real axis. And so that that certain interval on the real axis is called the absolute interval for absolute stability. And so we will define those two as well. Right, so the region of absolute stability, right? Right, so the region on which the method is absolute stable. So obviously that should be a region of Q, or basically a complex plane, that is called the region of absolute stability. So you can see that. So since Q is a complex number, you will always have a real and imaginary part, right? And then you will have the region of absolute stability, right? So this you can plot according to the numerical method we are working on. Okay, so then the interval of absolute stability, right? So if you have a region, right? So if you have a region, then there is obviously an interval, right? So on the real axis, right, there will always be an interval when you draw a region on the uh, real complex on the complex plane, real imaginary axis, right? So then right, so the interval on which the method is absolutely stable, right? So once you draw the region, you will have an interval like this. So obviously that interval is called the interval of absolute stability. Right. So now what we are going to do is we are going to see an example on how you can determine the region of absolute stability and interval of absolute stability, right? So that is the that is what we are going to see next, right? So obviously we will start with the very simple numerical method, which is Euler method, right? So that is a one-step method. So we will see the region for absolute stability for an explicit Euler method, which is the most simplest one, and then you can do it for implicit Euler method and other methods as well. Okay, so example. So this is the explicit Euler method, right? So we can find the region of absolute stability as well as the interval of absolute stability. So you can notice that A1 is 1, A naught is -1, B naught is 1, B1 is 0. Okay, so you can easily see rho of Z is equal to Z minus 1 and sigma of Z is equal to 1. Right, so that's obvious. You can just write down the polynomials. Okay, so you have rho Z is equal to Z minus 1 and sigma Z is equal to 1. Right, so that are those two are the first and the second characteristic polynomial. Once you do that, then you can find this. So that's clearly Z minus 1 minus Q. Q times 1. So that is Q. Okay, so you can easily find the root of this polynomial. Right? So this is obviously, b minus 1 plus q, right? So then obviously if you find the root, it is 1 plus q. Right, so if you find the root, then obviously what the Dahlquist root condition says is the root of this stability polynomial should be less or equal to 1. Right, so obviously this is a simple root, so there is no question about equal to 1 and repetition. So simply absolute value of q is less or equal to 1. Then clearly you can say that minus 1 is less or equal to 1 plus q less or equal to 1. So q is minus 2 less or equal to 0. Right, so q is a complex number whose value is in between minus 2 and 0. Right, so clearly it should be a circle of length 1 and centered as minus 1. Because it should go between 0 and minus 2. right? So Q will be a circle between 0 and -2. Right? So in the complex plane. And this will go from -I to +I, right? So that's known to you. And then by looking at the picture, clearly you can see that, right? Right, so the interval of absolute stability is closed interval from -2 to 0. Right, so this is how you find the region of absolute stability. Okay, so these are simple examples. So simple numerical methods, so you can easily work out the region for stability. Right. So as a homework, you can try. Right, similar type. You can always write down the stability polynomial and factor it out and find the roots of the polynomial and then apply the root condition, and then based on that you can determine the region of absolute stability, or at least you can determine the interval of absolute stability. Right? So these things you can do it as a homework. Right. So now what we are going to do is we are going to see different method to draw the region of absolute stability, right? Because here it was very simple, because I know it is a complex number and it stays between -2 and 0, right? So since I know the complex plane, I was able to see that okay, it should be a circle centered at -1 and with the radius 1. So any number, right? So any q falls in between this circle will satisfy this condition, right? So that is because of because we already know the complex plane, and because we already know about complex numbers, we are able to figure it out without any work done, right? Just by looking at the range for q, we just figured it out that okay, it is a circle centered at -1 and with the radius 1, so that it goes in between, a circle lies in between 0 and -2. So that's done without any extra work. Right? But even I think when you go for midpoint rule or something, you might have a little difficulty in figuring out the region, right? So if you go for higher order methods, then it becomes a little more difficult to determine the region, right? So in order to see that, we have to derive, or we have to find out a different mechanism to determine the region, right? So this is the standard way of getting the region. But from this line, right, we may need to figure out the region by using a different method for higher order or higher step method, right? So that kind of a derivation method is called boundary locus method. That is what we are going to talk about next.
Yeah.
It's called boundary locus method.
But you say number, Navaratri. Olha, muito bom isso também. Posso ver tá, mas
Okay, so these are just the repetition of what we have learned. Right? So the first thing is, you know that for all q in the region, the method is absolutely stable. Right? Second one, as I told you earlier, we choose lambda as a complex number and we set q as h lambda, so obviously q is a complex number. And then because of this q, the roots of this polynomial pi will have some parts of q in them. Right? So if they have some parts of q in them, then obviously they can be written in the complex form, right? So a plus ib is one of the forms. Cos sine theta plus cos theta plus I sine theta is another form, and then r e to the power I theta is another form of writing a complex number, right? So obviously you write with 0 less or equal to theta less or equal to 2 pi. Right? So this is a form of writing a complex number. But we also have, for absolute stability, right, the roots must satisfy that absolute value of the root must be less or equal to 1. So here the absolute value of this root is r, so that's obviously less or equal to 1. because r is less or equal to 1, absolute value of r is less or equal to 1, right? So you can always write the roots as e to the power I theta, or basically z is equal to e to the power I theta. So in that case, you can see that basically the boundary, right? Okay, so because r is less or equal to 1, then absolute value of r is equal to 1 is the boundary. And when absolute value of r is equal to 1, obviously you can write the root as, right, e to the power I theta. Right? So then the root on the boundary is written as e to the power I theta. So if you solve this, or if you find this root, or if you find this theta, then you can write down the, or you can draw the boundary quite easily, right? So if you find all these roots, right, and then figure out these thetas, then you can easily draw the boundary. So the idea behind boundary locus method is, because of these properties, right, because the root is a complex number, and because the root on the boundary, it has a unit length, right, we can write the root on the boundary as e to the power I theta. So now you have one variable theta only. So you can solve the polynomial for theta, and then you can figure out the boundary by using that theta. Once you draw that theta, or once you figure out the theta, you can draw the region, and that region gives you the absolute stability region as well as the interval of absolute stability. Right? So this is the idea behind drawing the boundary by using the values on the boundary. So this is called boundary locus method. Okay? So because we use this, right? Okay, so because on the boundary, the Q will take the form rho e to the power I theta divided by sigma e to the power I theta. So this is how we are going to find the region of absolute stability, right? By solving this kind of e to the power I theta form. Right? So let us see an example where we will consider a slightly difficult two-step method, right? And then try to find the region of absolute stability for that method. Okay, so the method is yn plus 2 plus h over 2 into 3 10 2 plus f of n plus 1. So obviously you can see that this is a two-step explicit method. So this is it. Okay, so you can easily write down what is A, B, and C. Oh, sorry, A1, A2, and A3. A naught is -1. A1 is 0. A2 is 1. B naught is 3 half. B1 is half. B2 is 0. Right, so these are your constant coefficients. A naught A1, A2, and B naught B1, B2 are your coefficients. Right. So then you can write the first and second characteristic polynomials as well. Right. So you can easily write, rho of z is equal to z squared minus 1, and sigma of z is equal to half z plus 3/2. Okay, rho and sigma, you know how to write this. Right, so once you write this, then you know on the boundary, right, we have a formula for Q. Because of this theory, we have a formula for Q. Right, so on the boundary, Q is rho e to the power I theta over sigma e to the power I theta. Right, so once you do that, then you can simplify this. Right, so now it's all simplification. So let me work it out. So Q is equal to rho of e to the power I theta. So e to the power 2 I theta minus 1 over sigma e to the power I theta. So 1/2 e to the power I theta plus 3/2. Right, so this is the formula. Okay, so this you have 2 e to the power 2 I theta minus 1 over 3 plus e to the power I theta. Right, so you multiply by 3 minus e to the power I theta. Sorry, 3 plus e to the power minus I theta. Right, so if you multiply this, you get some kind of a simpler form. Right, so do this, you get 2 into 3 to the power theta. Work it out. And so minus 3 plus e to the power I theta minus e to the power I theta divided by 3, 9 plus 3 to the power I theta plus 3 to the power minus I theta plus e to the power I theta minus times e to the power I theta is 1. Right, so plus 1. Okay, so now what we are going to do is we are going to rewrite this as cosine theta sine theta form. So now come trigonometry. Basically, this is 2 into 3 to the power 2i theta plus 6 to the power I theta uh, plus minus 6 to the power minus I to the power minus I theta minus 3 over 10 plus 3 times e to the power I theta plus e to the power minus I theta. So this is what you have. So now you write cosine theta plus I sine theta form. Okay, so you write this into cosine theta plus I sine theta form. So basically you have q as 2 times 3 into cos 2 theta plus bi into sine 2 theta plus yeah plus cos theta plus I sine theta cos theta plus I sine theta minus of cos theta minus I sine theta minus 3 the whole quantity divided by 10 plus the sine theta plus I theta plus cosine theta minus I sine. Right, so you write e to the power I theta as cosine theta plus I sine theta, the trigonometrical representation of complex numbers. Okay, so now the rest is trigonometry work, right? A-level trigonometry. So I'm going to leave it for you to simplify this and try to find this in the form, right? So try to simplify this, right, and write this down in a form x plus iy. Right, so basically this will have some cosine thetas and sine thetas maybe. So and this will also have some cosine thetas and I sine thetas, right? So this is just a level simplification. You can work it out and see what you get, right? So let me write the answer I have here, but I am not sure whether this is right or wrong. You can check this. Okay, so if you simplify by using whatever the trigonometry identities you have studied in A level, you should be able to get an x and y here such that this q is written as a complex number x plus iy. So once you know x and y, then you can draw the x and y in complex plane and then simply you can draw the region, right? So any complex number which satisfies these values for all theta between 0 and 2 pi will provide the region of absolute stability, right? So you notice that with 0 less or equal to theta less or equal to 2 pi, right? So if you draw this x and y, right, on an xy axis for all theta between 0 and 2 pi, you can draw the region, right? Now, if you want to find the interval of absolute stability, right? So, if you want to find the interval of absolute stability, what you do is you set y is equal to 0. Right? So, if you set y is equal to 0, then you get 2 sine theta into 3 times cosine theta plus 1 is equal to 0. Okay, so when you solve this, you get sine theta times 3 times cosine theta plus 1 is equal to 0. So this gives you sine theta is equal to 0 or cosine theta is equal to minus 1/3. Okay, so for these two sine theta and cosine theta, so there are two values, right? So here from this you will get theta is equal to 0, right? And from this you get theta is equal to cosine inverse, right? So from this you will get another theta, right? For this theta, you can find value for x, and for this you can find the value for x, right? So you will have two values, and those two values will give you the interval of absolute stability. Right? So this is how you see the region of absolute stability as well as you see the interval of absolute stability, right? So sometimes you may not be able to draw the region, but you can always write down the region in the form x plus iy, which is a complex form, so that that can be interpreted in a complex place. So this is how on a difficult case scenario, right, where you are unable to solve the roots for q, right? So basically, it is not easy to factor all polynomials, right? So if the polynomial is higher order, like z3 or z4 or something, then you may not be able to figure out the roots of the polynomial, right? So then it is difficult to figure out the Dahlquist root condition. So in that case, you may not be able to find the absolute stability region. So on those cases, you can use this idea that on the boundary, Q will take the form rho of e to the power I theta divided by sigma e to the power I theta, right? And then you can simplify that form and write this in a complex number form x plus iy or a plus ib form, and that will provide you the interpretation for the region. So that is how you talk about, or that is how you define the region of absolute stability. So we will stop here, and in the next class we will talk about another different type of linear multi-step method where we combine two different methods to produce the numerical approximation of a differential equation. Right? That is called predictor corrector method, right? Predictor corrector method, PC method, and then there is another method called predictor, evaluator, corrector method. So in the next class, we are going to see what those things means and how we can use that to evaluate the approximation of a differential equation in a better way. So that we will see in the next class.